So at MIT did his PhD with a quite a diverse also thesis committee going from economics, policies, and organic aerosol person. Then he did his postdoctoral fellowship at Stanford University in the Planetary Health and Human Health Department, School of Sustainability and Center of Innovation in Global Health. I have to say, Minghao had quite a run of successful papers the last 1.5 years. In 1 year, 2 proceedings of the National Academy of Science paper, a Nature paper, and a Nature Communications paper, and just before that, a Science Advances paper, which tells you he is on a really good streak and addresses very important topics. And one thing I discovered, you were a member of the last Access meeting, I believe, in 2023. That is the Atmospheric Chemistry Colloquium for Emerging Scientists and led by Ernie Lewis. And unfortunately, it has terminated. It doesn't exist anymore, but it's a great honor to be selected in that group. They select 20 to 25 junior scientists worldwide. It's very competitive to get into that. So we are really happy having you here as a new faculty member, and we are really curious what you tell us today. Climate change, impacts on air quality and human health, wildfires, drought, extreme temperature. Very hot topic.
Right. Thank you very much, Daniel. Let me perceive this thing seems to be working. Okay, great. Well, thank you so much, Daniel, for the very kind introduction and for memorizing all the long names of my past departments and institutes, which sort of tells you a little bit about, I'm just coming from a lot of places, and I'm trying to sort of combine insights from different disciplines to answer the questions we are interested in. So as Daniel introduced, I'm a new faculty member at SoMAS in the Atmospheric Science Division, and with a 50% joint appointment in the program in public health. So I'm very excited to be here. My office is in Discovery Hall. So if you ever want something, I don't have coffee machine or anything, but there is a hot water pot. So if you want a cup of tea, please stop by, and I would be love to touch it base. Okay, so I want to talk a little bit about my background first, just so people sort of know who I am, just beyond the name. So I was born and raised in Beijing, China. And there people are known, like people probably know this place for many reasons, but it was a bad place to be living in terms of the air quality. So that's why I sort of got really interested and excited in this topic in the first place. And then air quality sort of fascinates me because we care about them from the human health perspective, as well as it's a very interesting phenomenon that is not just a natural phenomenon, but it's really connected to our society, like how do we make energy and how do we develop our economy, for instance. Then, as Daniel mentioned, during my PhD, I was sort of trained as an environmental scientist and data scientist, where I learned about sort of machine learning, causal inferences, those kind of skills, and try to understand how different energy policies would influence air quality and the climate. During my postdoc, I then sort of bring in the perspective of climate change and then think about how climate change sort of influences all this. And this remains to be an important topic of my career here. And obviously, I'm now here. I'm very excited about the prospect of contributing at Stony Brook in SoMAS and public health. And so I'm sure this sort of people already know this kind of thing. So why do we care about this? So I study climate change and air quality. And one of the big motivations for me to going into this is from the health perspective. So on one hand, this is a quote from the World Health Organization. So climate change is the single biggest health threat of facing humanity in the century. So this kind of bold statement comes from that climate change is influencing a lot of things that has human health implications: heat waves, infectious diseases, food, water and air quality, migration, all of that. But on the other hand, we also know that air pollution is bad, right? So globally, air pollution is the #4 mortality risk factor. So leading to more than 7 million mortality every year, and the sort of #4 factor just after high blood pressure, tobacco dietary risks. So it's an important thing. So my work specifically looks at sort of this intersection between these two challenges, and I'll sort of be a little more specific in the next slide. And among many things, or sort of this is one of the underlying scientific questions that guide my research and sort of what I'm thinking to contribute to the different communities. So that is, how does climate change influence air quality and the related human health outcomes? So this is an important question, but there remains a lot of uncertainty among many of the key scientific questions. So this is a figure from a paper that's sort of published in Nature Climate Change. This is a little bit old paper in 2017, which the researchers were looking at how PM 2.5 related mortality would change under the different climate scenarios. So this is the RCP 8.5, which is the sort of extreme warming scenario. And the x-axis shows sort of the different models. So right, this is GFDL model, this is GIS model, for instance. And then you see this huge range of the potential, like the different models think really differently. Like some think PM 2.5 will really increase quite a lot under future climate scenario. Some think it doesn't change too much. And then some say it will actually decrease, right? So, and I'll sort of unpack a little bit that this is a result of many complex and compounded uncertainty in this. And it's important to know this because air pollution is really important for a lot of things, as we sort of just talked about. So understanding how climate change will move it has big implications for our scientific understanding of the physical world, as well as sort of prepare ourselves for thinking of future policies. So this is a quote from IPCC. So people who sort of work in the climate field, like you're familiar with this kind of statement, and all of them come with sort of a confidence level. So this is a statement saying global air pollution related mortality will directly attributable to climate change is likely to increase and partially counteract any decreases in air pollution achieved through emission reduction scenarios or whatever climate policies. So sort of the IPCC view of this is pollution is going to increase under future climate change, but this only comes with sort of a medium confidence level. And this basically means that we think this is qualitatively correct, but we have no idea sort of what are the numbers is. And I think this is sort of a very fascinating topic because climate change can influence air pollution through so many different ways, right? So there are potential ways through the natural mechanisms. For instance, climate change will increase or influence the risk for wildfires, dust storms, or direct influence the meteorology pattern, which all have implications for air quality. And then there are also human mechanisms. So because air pollution, or a lot of the air pollution is produced by burning fossil fuel, and climate change will have implications on how we use fossil fuel, and that will also influence our air pollution burden. So this is a sort of very complex picture, and sort of my research was sort of start to touch on a little bit of this, but I'm sort of broadly interested in basically everything in this slide and of course beyond. And for today, I'll mostly try to talk about wildfire relevant research and then a little bit on the energy system. So here are sort of the three key so I just talked about the big motivating question, and now the sort of the three slightly more specific ones. So one is how wildfire influence air quality and human health. The other is how climate change will influence sort of the atmospheric compositions and their implications for health. And then the third one is how do we address this, right? So what are the, so we're also interested in evaluating the effects of energy transition and climate policies on pollutant emissions, air quality, and human health. So I don't have the time to go through everything, but if anything on this slide excites you, please get in touch. Okay, so for today's talk, let me just back on one slide. So I'll just focusing on two specific studies. So one is not published under review, so I want to give people some fresh results. So I'll talk about this one under review study on wildfire. So how we quantify wildfire influence air quality, influence mortality, and how does climate change influencing that. So I'll maybe spend 20 or so minutes on that paper. And then I'll spend another 10 minutes to talk about this one published papers on energy sector. So how climate change influence energy sector, and then as a result, influencing emissions and air quality. And then in the end, I'll talk a little bit about some of the ongoing work. And also, I should say that people should feel free to interrupt anytime, including people on the Zoom. So I would like to like this to be a sort of interactive conversation. Okay, so on the first part, so this is our work looking at how wildfire influences air quality and mortality in the US. So this is more, so I'm mostly going to draw the results from the 3 papers. So the main results will be from this paper, which I led and is under review now. The other 2 papers are led by my colleagues at Stanford. I contributed to them, but I'll mostly just use them to set up the data set and the background. And then the meat of the sort of sandwich for this part will be this paper I did, or I led. And this is with a huge group of collaborators from Stanford, UCSD, GFDL, Harvard, etc. And there are climate scientists, economists, public health researchers, like a lot of people. Okay. So sort of the background on wildfires, right? I mean, people probably already know this, but wildfires are increasing in the US in the last 40 years, especially in Western US, but also really across the country. So here is a figure showing the percentage of forests being burned every year in Western US. And you can see this clear increasing trend, and this stops in 2020, which was a historical wildfire year. So about 2.5% of Western US forests burned in that year. And if you plot 2021 on this plot, it will be somewhere here. So slightly lower, but maybe something like 1.8% or something like that. So there is this big increasing trend in wildfires in Western US at least. But as I said, it's not just Western US. Really throughout, like in Great Plains in the Midwest and the East US, we're seeing that wildfires are getting bigger, and there's more of them like right now. So it's sort of a relevant topic across the country. People probably also know that wildfire is an important source of air pollution. So one of the main ones we focus on here is PM 2.5, those very small, fine particulate matters that can get deep into really can get deep into every part of you and cause all kinds of problems. So here are the 2 maps showing sort of the PM 2.5 concentration. Those are measured by the EPA air quality sensor. So those will be the data set you can see on your app, like on a daily basis. So this is 2020 September. There was a big wildfire complex in Northern California, Oregon, and you see the big influences. And then this one, I'm assuming people are relatively familiar with this one. This is last year when the Canadian wildfire smoke sort of made all the way down to East Coast, including New York. And then you can see this is clear influences on PM 2.5 and air pollution. Okay, so let me say a little word about PM 2.5 in general. So why do we care about them? So PM 2.5, there has this long-standing research on PM 2.5 is leading to all kinds of problems, including mortality and asthma, mental health issues, everything. So that's why, and those research or the pioneer, the research happened like in 1970s. And that's sort of the cornerstone of why we have the Clean Air Act. So in United States and really in many countries, PM 2.5 is a regulated pollutant. So there are clear guidelines on what PM 2.5 level should be, and there are policies trying to bring them down. So here is sort of, if we just aggregate all the PM 2.5 sensors across the US, and here is the sort of the figure we have. And so it starts in early 2000, where we have this robust record of nationwide measurements of PM 2.5. So what we see here is there's this big declining trend from 2000 to 2015. And this is a result of the Clean Air Act, that we have a more tighter regulation on automobile emissions, our electricity power plants is getting cleaner, all that kind of things. But then when we actually just look at the data, you would sort of see very clearly that around 2015, 2016, that PM 2.5 sort of starts to sort of stagnate. And in many parts of the country, it sort of starts to reverse. And so we are interested in what's driving this, and many people have done research on this. And what I'm going to show in the next couple of slides is trying to convince you that this is a result of wildfire, right? So it's really because wildfires influences that we are seeing this stagnation and reversal of PM 2.5 trend in this country. So how do we do that, right? So if we think about PM 2.5 in general, so it's a complex mixture and it's a result of many different sources. So wildfire is just one of them. There are power plant, there are automobile, there are industrial processes, so that. So how can we sort of separate or understand what's the source or what's the contribution of wildfire to PM 2.5? So broadly speaking, there are just two approaches. So one is using chemical transport models. So this would be process-based, physical chemistry-based models, so we can sort of simulate the wildfire influences on PM 2.5. Then there's the other approach, which is the approach we use here, is to sort of use this top-down approaches that we have satellite data and combine this with machine learning, so we can directly predict or quantify what's the sources of wildfire on surface PM 2.5. So let me illustrate our approach with sort of one example. So here you're seeing like just a time series plot for one air quality monitor in the US. And this is from August 2020 to November 2020. So the black line here is the raw measurements, right? So this is the total PM 2.5. You can see this is what the sensor measures, and you can see them again on your app. Our job is to understand what's the contribution of wildfire to this data. So we combine this with what I show here is sort of those gray dots and what we call them smoke day. So this is information based on satellite products. This is produced by NOAA. So essentially there are NOAA analysts who would literally look at the satellite images every day, and they would draw this kind of big polygons of where they think wildfire plume is and where are the wildfire plume influences. And we just label them as gray, so we call them this sort of gray dot if this monitor specifically is under the influence of plume on that day. So this is sort of the smoke day information. And then there is this blue line, which is what we call the non-smoke median. So this is calculated as an average PM 2.5 of the same monitor measured across all the non-smoke days. So there is variability in PM 2.5 on non-smoke days as well, but we just take the average. So this sort of is our sense of what non-smoke PM 2.5 look like at this monitor. And then we take the differences between the black line and the blue line. So this is the right line here. And this is our estimates of what wildfire smoke contributes to, right? So this is a particularly good example that you can see that when there's big wildfire, I mean, you really have a spike in the PM 2.5, and this spike is way above the average median of this location, for instance. And then that's our sense of what smoke PM 2.5 looks like. I mean, there's some assumptions involved in this, but this is a nice way and a widely used way to sort of think about what's the wildfire contributions to PM 2.5 here. So if we do this and then we redo the analysis I just showed you in the previous slide. So again, the black line is just the trend of total PM 2.5 measured in this country. And the blue line here is if I take the non-smoke PM 2.5 as sort of I derived in the previous slide, and this is sort of the trend of that. And what we see here is, so nationwide, there is this continuing declining trend if you remove wildfire influence or drop the influences of wildfire. It's particularly maybe even clearer for some of the Western states. Like for instance, in California, that if you drop non-wildfire smoke, you have this blue line here and this sort of declining. And really when you add back the wildfire smoke PM 2.5, like we're seeing this reversal or stagnation. So this is so that's one of the conclusion of this paper, that is wildfire really drive this stagnation of reversal of the PM 2.5 trend. The problem is we don't have monitors everywhere in this country, so that's why we have this data set. So this is led by Marissa Charles. So we now have this information, right? So we then use machine learning to derive a relationship between satellite images or satellite information and the smoke PM 2.5 measured at the monitors. So we have this relationship, and then we can apply this relationship everywhere in the country. So we can get maps like this. So this is our estimates of what wildfire smoke influences on PM 2.5 like. So the data set is at 10 kilometer and daily resolution. And then this is sort of the public version of the data. We are working on this updating this data set to 2023, so you will see the influences of Canadian wildfire, for instance. But this is the maps of from 2006 to 2020, and you can sort of see the hotspots of wildfire smoke, and then there's this clear increasing trend in wildfire-driven PM 2.5 pollution in the US. Okay, so it's increasing. So like from the map, you see it, and now if I just aggregate them all together, like it's increasing, wildfires increasing, and not surprisingly, wildfire smoke PM is also increasing. So why is that, right? So that's sort of the paper or some of the motivations of our paper. So there are three major reasons. So one is climate change. So we have warmer and drier climate. So that leads to more wildfires. And as a result of that, we have more wildfire smoke pollution. There is also this, especially in the Western US, there is this long-term fire and land management practices. So meaning that people have embraced this idea whenever there's a small fire, we need to put it off. So this sort of alter the natural fire dynamics. In some sense, you have a lot of accumulation of fuel on the ground. So that leads to some of the disastrous big scale wildfires. And then the third thing is people are living closer to forests. So this, in the academic term, this is called expansion of wildland urban interfaces. So people are living closer to forests, and that significantly increases the risk started by humans. So this will be someone camping in the forest, or they're driving along the highway, or whatever, and then there's some spark, and that increases wildfires. So those are the three big major reasons. And in this paper I'm going to talk right now, this under review paper we have, like we're focusing on climate change, right? So what's the role of climate change in driving wildfire smoke PM 2.5 pollution in the US? So there are the three main research questions. So how do climate conditions influence wildfire smoke PM in the US? What's the wildfire PM concentration going to look like under future climate scenarios? And then what's the mortality burden associated with wildfire PM under those future climate scenarios? So this is not an easy task. So essentially we have three tasks to solve. So on the first one, we need to understand how climate change influences wildfire. The second one is how wildfire influence PM 2.5 concentration. And then the third one is how wildfire PM 2.5 influences human health. Okay. So, I mean, I don't have time to sort of go into each of them, but broadly, we sort of try to make some contributions to each of them. And in some one is bigger, some one is smaller, but we try to make contributions to all of them. For the first one, we developed this statistical and machine learning methods, try to link climate variables to wildfire and wildfire emissions. In the second one, we use this satellite-derived data set I just talked about to try to understand what's the relationship between wildfire emissions and then the wildfire PM. And then the third one is to try to understand how wildfire smoke influence human mortality specifically. So I don't know if I have any of my public health colleagues. I guess Guanyu is here. I don't know if some of them is in the room or online, but let me say a little bit about this. So why do we think it's important to sort of understand this? So we have many good evidence saying PM 2.5 is bad for human health, right? So those are long-standing literature, and like we have some good evidence on this. But there are some hypotheses saying maybe wildfire smoke PM is different from some of the other sources. So because PM 2.5 is this complex mixture, and sort of different sources may be different and having different human health impacts. So this is one of the million-dollar questions in this field right now. I still don't think we fully know whether wildfire smoke is more toxic or less toxic compared to some power plant or vehicle emissions. But there are sort of two main reasons why we think they may be different. So one is from the chemical perspective. So again, PM 2.5 is this complex mixture. If you get this from wildfires, so the chemical fingerprints may be very different from if you get this from power plants or vehicles. The second one is in my mind more interesting, or maybe even more interesting, is that it also induces some behavioral changes. So wildfire is very spiky, right? So it's sort of most of the days it's 0, and then on one day it's 200 micrograms. and it's very visible, and people see it, people respond to it, and they respond in a way that maybe influence how wildfire can actually influence their human health. So maybe they stay at home more, or they put on a mask, or things like that. So that may change how pollution influences their human health outcome. So this may be very different if we're talking about like vehicle pollution, for instance. If you're someone living in New York City and you just get used to this kind of things, right? So you don't really make special plans or anything. So those are, again, we don't really know if it's going to be worse or better, but that's one reason why this could be potentially different. So we are going to directly estimate how wildfire smoke influence mortality in this. Okay. So this is a three-stage modeling strategy. So in the first one, again, we are building statistical model, try to link climate variables to wildfire emissions. The second one is we're building another statistical model that try to link wildfire emissions to PM 2.5 concentrations and accounting for wind directions and distance from fire, for instance. And the third one is, we are linking the wildfire smoke data directly to real county level mortality data reported by CDC, and we can sort of estimate how wildfire smoke influences mortality, like directly, not just taken from other people's estimates, for instance. Okay. So all the dots are gone in this figure, so I'm just going to let you trust me that our model performs pretty well. That like you were supposed to see that this is going to be like you should be able to see some dots here, and they align on the one-to-one line. Like one thing really interesting here is actually when we build this kind of models, we realize it's really hard to actually capture the fire dynamic at sort of fine spatial and temporal resolution. And then because there is a lot of randomness and stochasticity of fires, and some of this is not really driven by climate factors. But if you do aggregation enough, then we can see some of sort of the climate changes really having a big influences on this large scale patterns of wildfires, for instance. And also, I should mention, we are building models for the entire North America. So even though we only sort of look at the wildfire and the mortality in the US, but because of reason people are now well aware of that Canadian wildfire smoke can be relevant. So we're also building models to think about how different climate variables could influence wildfire concentrations in all parts of the North America. In the second part, we are linking this sort of building this very simple regression-based approach that we try to link fire emissions to the PM concentration in the downwind location, right? So for instance, here is like you have some fire emissions, and this emits, let's say 100 tons of some kind of pollutants. And then we try to link this to the smoke PM concentration data we derived and try to get this relationship. And we also let this relationship to take care of sort of the distance from fires and whether sort of, and the wind direction, obviously, like whether the location is directly downwind of fires or sort of upwind or other places. And then in the third stage, we look at how wildfire smoke influences mortality. So this sort of is a equation, but essentially we have county level mortality rate data, and this is at the monthly level. And then we look at this monthly level mortality rate and link this to the smoke PM 2.5 concentration at this county. So this sort of this epidemiology analysis. And then what we are interested in is whether this county has a higher than normal mortality rate if it experienced sort of a more wildfire smoke, for instance. So this is sort of this statistical epidemiological analysis. I can talk more about this, but we try to control for some of the baseline variables that could also influence mortality, which has nothing to do with wildfire smoke, for instance. So we have this big model. So when you put everything together, so on one hand, you input climate variables. So those are temperature, precipitation, wind speed, etc. And then on the other hand of the model, you have smoke PM 2.5 concentration and the mortality associated with it. So what I'm showing you here is sort of the map of annual mean smoke PM 2.5 concentration in the US. So this is 10-year averages. So this panel is historical, what our historical level is. So this is 2011 to 2020. And then the three maps here are our future scenarios. So this is in the year of 2050. And then the three climate scenarios. So from SSP 1 2.6. So this is the most optimistic scenario that we can reduce our greenhouse gases emissions. So we are going to have less warming perhaps. And then the 3 7.0 is one of the extreme warming scenarios. I'm not even showing the most extreme, which is 8.51. So you sort of get a sense of this. So it's clear that it's increasing, and many of the sort of the changes is in Western US. But because of this long-range transport pattern, so we're also seeing many changes in the Midwest. And then like you can't really differentiate the two colors here, but like there are also some differences in Eastern US. And then when we just calculate this population weighted, so just combine the small concentration with where people live. So this is sort of on average, or an average US person, what's the level of smoke PM level they exposed to. And what we're seeing is there's these huge increases by up to 2 to 3 times when we look at the future scenarios. I mean, one thing really interesting is that, I mean, there are not much differences if you look at 2030 or 2040 across the different scenarios. And that's sort of expected because, I mean, we know that, I mean, there are a lot of climate scientists in this room, but we know there are this sensitivity or memory of our climate system to greenhouse gases. So even if we like get rid of our CO2 emissions tomorrow, like we're still going to see quite a bit temperature increases in the next 10 to 20 years. And when this reflects on smoke PM 2.5, this is what we have, right? So you're going to see increases in smoke PM 2.5 regardless. And then maybe in 2050, like we can start seeing some differences if we reduce emissions more aggressive than in some other scenarios, for instance. And then when we sort of think about what is then the contribution of smoke PM 2.5 to total PM 2.5, so this is a very simple analysis. So we're just assuming that like non-smoke PM 2.5 is not going to change in the future, which is actually sort of a very unrealistic estimate because all our thinking is now all the other like energy related PM 2.5 is probably going to decline quite a bit because we're moving away from coal power to renewable energy anyway. So in that sense, the wildfire PM contribution is actually going to be even higher. But even if we just take this conservative assumption saying, well, the non-smoke doesn't change, the smoke will account for a lot of PM in the future climate. So in the Western US, sort of more visibly that about 60% of Oregon's PM 2.5 is going to come from wildfire in 2050. And this number right now is something like 20%, for instance. And then across the US, right, so the number right now is 5%, right? So wildfire is contributing 5% of total PM, and this number is sort of tripling to 15 to 17% in the future. And this is big changes, obviously, and it has all kinds of implications on how we think about how should we regulate PM 2.5, because right now, I mean, I can talk more and more about this, maybe over lunch or in the Q&A, but right now, wildfire PM is not even regulated. I mean, this is often seen as an exceptional event that is beyond our human control, that we can do anything to control for it. But maybe it's justifiable with 5% contribution, but then if it's 15%, I mean, like, we can't just hide our hand to say, oh, we're not going to do anything about it. Again, happy to talk more about them. This is our empirically derived mortality function. So how mortality respond to wildfire smoke, right? So you see, I mean, this is annual mean smoke PM 2.5 concentration. So there are these increases. So we see mortality rate increases if this county has more wildfire smoke. So for instance, if you look at the 6+ bin, so this is saying if a county has an annual average of 6 microgram smoke PM 2.5, so this is about the level of sort of what California experienced in 2020. like this county will see a 6% more mortality rate. And we are talking about all-cause mortality, right? So this is huge number if you sort of do this calculation. And then when we sort of combine this response function with our future estimates of wildfire smoke, so this is our historical number here. So like every year wildfire smoke is responsible for about 16,000 premature mortality in the US, like historically, and this number will increase to 24 to 28,000 in future climates. So that's about 8 to 12,000 more. So that's, again, big numbers. What's really interesting if we look at the spatial pattern of this, so what I'm showing here, this is for each, so at the county level, what are the extra smoke PM related mortality comparing 2050 to today? And so this is sort of at the county level. I mean, you see all the big hotspots in sort of Western US, especially in some of the populous counties in California. But if we actually do the calculation, over half of the mortality happened in the east of this dashed line, not in the west of this dashed line. Obviously, that's just because more people live in the eastern US. So even if you have a little bit of wildfire smoke, that's translated to a lot of mortality. So historically, about 2/3 of the mortality happened east of this line. And then in the 2050, because there's more wildfire smoke increases in the west, this number changes a little bit, but still about 42% of the mortality happened in the east of this line. So this is definitely not just a Western US problem. Like this is, so we should, I guess I'm just convincing my colleagues here to, we should care about this, and we should research and write proposal about this problem. Okay, this is just on the first part, right? To conclude on this, so we built this sort of data-driven estimates on how wildfire smoke PM 2.5 going to look like under future climate scenarios, and people are welcome to use this for all kinds of applications you have in mind. I mean, this is going to be I mean, I didn't really talk about this part, but if you monetize the mortality I showed in the previous slide using EPA standard approaches, so we can sort of have a monetary estimate of what's the climate change influence on US society through wildfire mortality. And if you compare this or monetary estimates to all the other estimates people are talking about, like those including like agriculture or heat wave mortality, labor productivity, crime rates, all this kind of things, like we end up having this conclusion that wildfire smoke is the biggest one among all of them. I mean, there are a lot of assumptions involved in all this, but this talks about the magnitude that wildfire smoke or climate-driven wildfire smoke is really like maybe one of the most important consequences of climate change in the US, and we should care about this. And then there's the adaptation message that we are going to see a lot of increases no matter what, so we should figure out strategies that we should adapt to that. But still, mitigation matters for this, that if we reduce our greenhouse gases emissions, that there are still some differences, and we should absolutely do that. Okay, I think I'll pause here for a second, so if people have questions on this, because I mean, I'll shift to the second one, which is related but very different topics on drought and energy systems. Yeah.
You have a slide, the population exposure and future scenarios that showed for different pathways. And in one of them, I noticed that there was a state by state cutoff. I was wondering why that might happen.
Yeah, that's a great question. So this is, I mean, I don't want to go way back, but there is a little bit state cutoff because in our fire smoke model, I mean, because we know that there are regional heterogeneity in, like, if you burn, like, let's say 1 acre forest here, like it may have very different impacts on PM 2.5 if you burn like same 1 acre but somewhere else, like because of the atmosphere is different and the vegetation, that's all different. So like we take a sort of a lazy approach that we just want to approximate this relationship by estimate separate models for separate regions. So there is a little bit like manual cutoff here, like if one state belongs to this region and one state belongs to that region. So it's not natural. So it's sort of like it's an issue with our model in some sense, which I think we hope to improve in the future versions. Yes.
So actually, I have two questions, but I know you want to go on. One is, your assumption is that there's going to be the same amount of vegetation and that there isn't going to be any management and controlled burns that might reduce vegetation. And my other question is, what do you think the percentage of PM 2.5 particles that are organic are compared to all of these smoke and other?
Like on the second question, like is organic, like it's the composition different? Is the question about the compositions or?
Yes, composition.
Okay, yeah. Yeah, the second question is
1%, I mean, just some, is it only 1% of the particles are pollen or?
Oh, I see. I see. Yeah, great question. So on the composition, I mean, that's also a hot topic, and I know Daniel, for instance, have done research on this, but most of them is organic pollutants, and we're talking about like at least 95%. And we're talking about the mass space, right? So about 95% of the PM 2.5 mass during wildfire smoke is some kind of organic aerosols. I mean, this is an entire field trying to figure out what's in that organic aerosol, because there are different organic aerosols. Some of them are primary, directly burned. Some of them are secondaries or formed through chemical reactions, all that. But yeah, so most of them is organic. And that's obviously very different from if we're talking about like vehicle pollutant, like many of them are nitrate, for instance, or from power plants from sulfate. I want to jump on something.
Yeah, let me follow up on Josie's great question. In the data on the trend of PM 2.5, somewhere, at least going into the future, there will be an underlying increase in organic PM 2.5 from the increase in BVOC emissions from vegetation, but BVOCs don't yield black carbon. So I'm wondering if there is any data that shows that the fraction of the PM 2.5 that is black carbon is increasing, something that helps chemically support the notion that the leveling off is entirely due to wildfire.
Yeah, that's a great question. Let me finish the composition part, then come back to the first question.
You're not, I mean,
Yeah,
we wanted to talk about other things today, but just,
sure. Yeah, no, those are.
Give another seminar on that.
Those are great questions. So there is some studies on black carbons or specific, and I don't think it's sort of at the national scale as our paper, but I mean, I think that's an interesting idea to think about the sort of like from the chemical composition wise, can we do a better job to establish that the wildfire is responsible for the stagnation of that. And let's quickly on the fire management, because that's a great question. I mean, that's a question that all the reviewers want to talk about. Like what our assumption is not no land management, is the land management stay at the level of historical data, right? Because the relationship is derived from the historical data. So we're talking about or this is under the assumption that we are doing the same kind of land management and prescribed fires, all that, which may not be a good assumption, but we are isolating the differences from climate change from that perspective. I'll move on to the next part, but happy to come back again. So very quickly, I mean, this is already published, so people can look it up. But I want to sort of talk a little bit to give a flavor of the other part of the research agenda I do, which is sort of more from the energy system perspective. So in this paper, we're looking at how drought and climate change related droughts influence the electricity system, and then its resulting impacts on emissions, air quality, and in the Western US specifically. So I'll skip this one. So drought is a big problem in Western US. So there are many pathways that drought can influence sort of electricity system. So in Western US, I know hydropower is also a big part of our state's, New York State's energy supply, for instance, but in Western US, 30% of electricity is generated from hydropower, So obviously drought influences that, and then that it makes there's less hydropower that we can use. Drought often happens at the same time with heat waves, and heat waves increasing our energy and electricity demand. Drought also can lead to more wildfire smoke. So, and then wildfire smoke can sort of reduce the efficiency of solar energy panels, and that also have implications. And finally, many of the fossil fuel power plants, like coal power plants, they are water-based. They need water for cooling purposes. And so if there is not enough water, then they can't run at their full efficiency, and that also has implications. Okay, so in this work, we're looking at how, I'm just going to go relatively quickly on this project, but we are looking at how drought would influence the generation and then emissions from all the fossil fuel power plant in the Western US. And here is sort of the map of showing that, right? So the red dots are all the natural gas power plants, and the yellow dots are the gray dots are the coal power plants. And then there's a little bit other color, which are mostly biomass based. So this is a statistical analysis that we basically try to look at the same power plant and see whether the fossil fuel power plant, whether they generate more during drought or not. And the answer is yes, right? So this is showing that, I mean, under some drought condition, right? So the California's fossil fuel power plant essentially generate 30% more electricity compared to the months or years when there's not much of drought. There is also this interesting sort of regional pattern. So because the electricity market is connected, right? So for instance, California is importing electricity from like Oregon or from Utah all the time. So we're also seeing that when there is a drought, for instance, in Northwest or in the Southwest, like we are also seeing that in California's fossil fuel power plants, like they generate more, right? So this is sort of showing by this two bars, right? So if there's a drought in Northwest, for instance, California, and it generate like 25, California fossil fuel power plants generate like 25% more electricity, for instance. And then there is sort of the similar idea for Northwest and Southwest, but let's just look at California, for instance, right? So this is, again, the fossil fuel power plant generation in California, and sort of is ranked by the different months, right? So this is essentially the driest months ever happened in this historical period. So this is 2001 to 2021. So relative to the average, right? So those fossil fuel power plants generate something like 40% or 35% more electricity, and about 20% of them is through, about 25% of this is what we call the South effect. So this is California drought effects on California electricity generation, and then like 30, like the other is sort of the regional effect, like through the regional patterns I just talked about. So I mean, like, I guess this goes without saying, like this. So when those fossil fuel power plant generates more electricity because they are coal-based or natural gas-based, they emit more emissions. So here we're looking at sort of whether we can detect this through air quality sensors, right? So here is sort of give people an idea, right? So let's say there is an air quality monitor. This is sort of our right triangle here, and all the colored dots sort of next to it are all the power plants to it. So we're interested in, like, if we know those power plants will generate more electricity during drought, like, are we able to see increases in PM 2.5, like measured by those monitors during drought? And the answer is yes. So actually, like from the historical data, we're able to see that, like, if this is an air quality monitor and it's next to a power plant, which we think is generating more during drought, like we're seeing larger increases in PM 2.5. And honestly, that surprised me quite a lot when we first see this, because we're unsure whether we can see this with the real actual PM 2.5 data, because there are so many drivers of PM 2.5, all that, but like we're able to see this at least a little bit. So then we do this sort of cost-benefit analysis in some sense, right? So we have all this drought-induced emissions from PM 2.5, from CO2, and we sort of put the dollar values on them. And we can compare this to some of the previous damages people talk about from this channel, right? So this would be like when you have less hydropower reduction, you have to use the more expensive natural gas power plants, all that, and that has economic costs associated with it. So here, like if we take the magnitude of our estimate, that's sort of higher or comparable to some of the previous estimates. This is, we then look at how this influences or how this evolves under future climate change. And then we only look at this for Western US, and then the conclusion, I just skipped that slide, but the conclusion is because all the climate model project there's going to be more drought in Western US, so we're going to see this sort of at the bigger impact under future climate change. So that's sort of the paper. That's a very quick overview. But then I think what's interesting is I want to show this slide, which is, even though we only focus on the Western US in that paper, but this is obviously sort of globally relevant because on one hand, many countries use a lot of hydropower, right? For instance, a lot of African countries, Amazon countries, and elsewhere. And then on the other hand, climate models project that there's going to be some reduction in runoff or some drought risks. And that's a big problem. So this is sort of globally relevant. So that's we are interested in doing more analysis along this channel, for instance. Just my last slide, I think. I'll skip this one. So just some of the ongoing work. So some of them are under review, some of them are sort of ongoing. So if you ever interested in collaborating or want to know more, please get in touch. So on the wildfire perspective, right? So we are doing work on how do we measure wildfire influence on PM. So this is sort of looking at how machine learning type of methods compare to the more traditional air quality models, for instance. I'm also interested. I'm working with undergrads who's helping with try to understand how wildfire influence ozone pollution as well. Right? So far, we only talk about PM 2.5, but there's also ozone. And then fire is also different, right? So there is the wildfires, and then there's the human ignited sort of the prescribed fires that used to manage forests. And then we're also interested in whether they give you different implications for smoke or air quality, all that. On the climate side, so this is a project I'm very excited. I want to talk more about to people who actually work on this is how extreme temperature influences PM 2.5. So when you look at the actual sensors data, we're able to see that on super hot days, like days above 100 Fahrenheit, for instance, you see PM 2.5 doubling or tripling compared to days with something for instance, 15 centigrade, 15 Celsius, for instance. And that's puzzling that we don't fully understand the mechanisms, and they have big implications for human health. This is led by my first year PhD student at SoMAS, Deyang Chen. He's interested in looking at how global climate change will influence energy emissions, sort of expanding on what we did for Western US and also looking beyond the drought, but also look at different climate change influences. This is my email, and this is my Twitter, and my office is again 125 Discovery Hall. So if you ever want to reach out, that would be great. Thank you, and I'm happy to take a few more questions.
Tomorrow, we have maybe 5 minutes for questions.
Yeah, Nick.
Hi, thanks for provocative and exciting talk. I'm interested in the relationship of PM 2.5 with human mortality. And is that based on a linear no threshold model? And I worry about linear no threshold models because living organisms have adapted over millennia to be able to tolerate modest levels of all sorts of nasty substances, radiation, for example, and do just fine at low concentrations. And then as concentrations go up, there's can be mortality. And so I'm wondering, in this case, if the PM 2.5 is, if the assumption is made that any increase in PM 2.5 is going to lead to an increase in mortality. And if that's the case, I want to know how solid that assumption is.
Yeah, that's a great question. So to put it sort of simple, what we do is a non-linear no threshold model. But sort of the no threshold comes in that we basically, I mean, there's no threshold. We didn't specify any threshold in the sense that we just link county level PM concentration to county level mortality. So if there's no effect at the low level, then that's fine. That's what the model will tell us. But then the model tells us like even at the low annual concentration, there's some effect, and that's sort of statistically significant. And it's in the model, this is sort of nonlinear. I mean, we can come back to this, but I mean, I think one reason driving this result is because we're aggregating PM to annual level. So even though the annual concentration is super low, it's like a result of like 3 days of very high concentration. It's just when you average them out, you get some very low annual concentrations. I mean, we can talk more about why we did that, and that's mostly because we were doing this future projection, and we're only comfortable projecting annual level at future, not at daily level, because that's just impossible to know. Like, or I mean, at least in the current model, it's very difficult to know that. Like, we are only comfortable predicting annual mean smoke concentration level under future climate. So that's why we chose that house model specifications. Yeah.
My question is also kind of related to the mortality. What would cause higher mortality with higher PM 2.5 concentrations? Like, was the mortality based on if someone's driving their car, PM 2.0 level was high, they get in a car accident, they die? Was it really due to the PM 2.5 being 8 micrograms per cubic meter versus 4?
Yeah.
Visibility is roughly the same. Is that death really related to the PM 2.5? So I guess what is the relationship between the cause of the death and the actual particulate?
That was a great question. I mean, we didn't do much cause specific. There was this actually one recent paper just came out in PNAS like yesterday, and they were looking at the cause deaths. The main reason is cardiovascular related mortality. I mean, this visibility is a really interesting question. I don't think people have really looked into that, but it seems like it's probably going to be a very small fraction of the total mortality, driven by sort of the actual physiological influences of that. I mean, that's also related to the bigger epi way of thinking of this, and which is, I mean, we don't really pin down this to the actual mechanism. Like, it's sort of a statistical relationship that when there's more wildfire smoke, you see more mortality. And we try to be careful controlling for some other factors that can drive this. So it's possible that wildfire smoke directly lead to mortality, or they exacerbate some existing conditions, and we will probably want to call that wildfire mortality as well. Is there a question? Yes, go ahead.
That's a great topic. I'm kind of curious about the smoke specific PM 2.5 and the regular PM 2.5. What are you talking about? Do you think which one is more toxic? Which one is more like, helpful for cattle? I think that's a very good topic of it. Thank you.
Yeah, that's as I said, I think that's $1 million question in the field right now. I mean, there are a couple papers you can see floating around and get cited all the time that saying wildfire smoke is more toxic. They often tends to mean the one widely cited paper is one did in Southern California, which they link wildfire smoke to I think asthma rates or some hospitalization visits, and they find the relationship between 1 microgram of wildfire smoke is like 10 times more than the effects of 1 microgram of other sources. That's the paper cited all the time. I don't think that's actually right. I mean, because there are some statistical enough details you can look into that. It's complicated. I don't think we have a definitive answer whether wildfire smoke is more toxic or not. I mean, one of the reasons is because the reason I mentioned is wildfire smoke is visible. You can see it, and people respond to it. Like, people, when they see big wildfire, they don't come to home. They don't come to work, and maybe that help reduce their exposure to pollution and then reduce mortality effects. I don't know. I think that's our active questions.
Okay, maybe last question, Minghao, yeah?
Yes. So in terms of public policy, cutting greenhouse gases certainly should be done, but it's difficult. However, controlling the forest might be a, say, more feasible method. So as Josie mentioned, this controlled burning, are these studies to show, say, offsetting pattern of fire controlling to offset the climate change impact on fire?
Yeah, I mean, that's another great question that we have some preliminary work going on there. I think, so the land management or the control burn is perhaps the only effective policies people actually talk about in terms of the regulate this wildfire pollution, because it's not like power plant, you can just put filters on forest, right? That's not possible. But there are also a lot of uncertainties related to that. Like one is those control fires are fires as well. So they contribute smoke. So there is sort of basically this trade-off. And it's an understudied topic that people on a small scale, people tend to think that the control fires are less bad than the wildfires because people know where it's happening. So maybe they can sort of time it to better time to do that kind of things. But there's still much unknown. Also on the benefit of it, the benefit is if you do small control burns here, that help reduce the likelihood of future fires. So that's also, I mean, that's not really well studied in some sense. I mean, there's like, we don't know how long the benefit can last, right? Like if you burn here, like how long can it reduce the future wildfire risk for 5 years or 10 years or so? But I mean, those are important questions to be studied. We try to do some of that, but it's a much bigger field. But I think you're absolutely right that that's probably the most relevant and realistic policy that to think of in terms of actual reduced wildfire smoke.
Yeah, and also it could be made like climate smart, right? You do control the burns before the rain event.
Yeah, absolutely.
And when the wind is blowing, say, to the ocean.
Exactly. Yeah, exactly. Yeah, absolutely.
Or you do selective cutting, or instead of burning, it seems burning,
Yeah.
we should cut the forest earlier
Yeah.
and then.
Pay all the forests and that would solve all the problems.
Well, that was not the statement, but you could do that smart with albedo too, because forest is not necessarily always climate positive. So if it's brighter, you win more than having a forest. So anyway, with that note, we go into lunch. As usual, in the friends room, and thank you, Minghao.
Thank you very much.